Hi guys. Before we move on to the next piece of theory, I do just want to do a quick review of the last concept that we explored, which was considering the difference for an inequality statement. So we said that this generally works nicely if we are given variables that are positive for us to consider. And in this particular question, we can see that both S and R are values that are equal to or greater than 0. So they're both positive numbers. And this is a show question. So even though it is only worth 1 mark, we do need to make sure that we write all of our working out down so that it's explicitly clear for the examiner. And our technique when we were considering the difference was to bring everything over to the left-hand side together and subtract the statement that's sitting on the right-hand side from what was already sitting on the left. And we can see that this gives us a statement where the left-hand side should now be a value that is also greater than or equal to 0. Okay, so to begin solving this, the first thing I'm going to look to do is to remove the denominator of 2, so I don't have to work with any fractions. So I'll multiply everything in this statement now by 2, including the 0 that's on the right-hand side, and we will get the numerator on the top of that fraction minus 2 lots of that square root, which is greater than or equal to 0. Okay, so now we have a statement where we're considering a sum of 2 positive numbers and subtracting from it 2 lots of a square root. So I'm just going to do a little bit of rearranging here to see what I can do with this statement. What I want to do is get down to something that I know is definitively positive. So I need to sort of think about things that will always be greater than or equal to 0. The nicest thing for me to be able to simplify this expression to is a square value, because we know that anything squared is always going to be a positive number. So if I can get my inequality statement to look like that, then I've proven this statement. So I'm going to rearrange this statement so that the surd is in the middle. And we'll see why in a second. Okay, so I've also split that surd in the middle, and remembering that this expression here means that I have 2 lots of the square root of r multiplied by the square root of s. And if I go one step further, we could rewrite r as the square root of r all squared, because they will cancel each other out and just leave me with r, minus 2 lots of the square root of r times the square root of s, plus the square root of s squared. Okay, so looking at this statement, does it look familiar? Does it look like something that we could work further with? The part that I like about it is that I have now introduced some square values, which I know to always be positive. But if I also now consider this statement that's sitting in front of me, I have a square value minus 2 lots of that value multiplied by another value plus that second value squared as well. So this gives me a trinomial that factorizes beautifully into the difference of those 2 values squared. So I can factorize this statement, and I'll have the square root of r minus the square root of s all squared is a positive number or equal to 0, which is a statement that is always true. We have a single square number, and it's told to be either a value of 0 if r and s are the same value, which they can be because we're told at the top that both of them could equal 0, or the difference between the two is a square value that's always positive. And so hence we've proven the inequality, and the statement holds true. So this leads us on to the next piece of theory that we're going to explore, which is utilising squares to be able to prove these statements. And this first example that we're going to have a look at is using a very similar idea to that past HSC question. So this concept generally relies on the idea of us factorising something into a perfect square as we know that square value we can then state as a number that is always positive or zero. Okay, so for this first example in front of us, we are being asked to show or prove that again we have two variables that are positive or equal to zero and a beginning statement. So if we know that A and B are two values that are positive or zero, then the first thing we're asked to do is to show that this statement that I've just highlighted holds true. We're then asked to perform a second step in this solution, and it gives us the word hence, meaning using this previous idea, now show a second statement also holds true. Okay, so let's start with the first statement that's been given that we've highlighted in yellow. So we've got this on the left-hand side, and then this statement on the right. Okay. So the idea being, I will start this question exactly the same way. I'm going to start by considering the difference between the left-hand side and the right-hand side. So we will take this value that's sitting on the right and move it to the left. And so we will have the difference between this term and this 2a squared b squared. And that will therefore be a positive value or equal to zero. Okay, now just as we did before, we need to try and simplify this statement somehow. And as we said, we're looking to try to factorise these things into perfect squares. So the first thing I'm going to do, I can see that they both have this factor of AB. So I'm going to divide it away. And that will leave us with just that set of brackets, so the a squared plus the b squared from the first term, minus two lots of AB. Okay, which looks very similar to the previous question that we just answered, in that we have a square number minus two lots of that number multiplied by another value, plus the square of that second value, which can be factorised into this perfect square, giving us a value that is always greater than or equal to 0. So that's the first bit proven. The second part of the question now asks us to use that idea to show that this second statement also holds true. So this gives us a hint that the second part of this question should fall away fairly quickly. So instead of considering the difference on this new expression again and going through that whole proof, which will certainly work, but this question suggests that there's a quicker way for it to happen. So I'm going to take this statement that we've now proven to be true, and I'm going to make a substitution into it. So I'm going to say, let's let all the a values now equal the square root of x. And we'll let the b values equal the square root of y. And I'm choosing these two values because of this third term that is sitting in the expression I'm now trying to prove. So if we now substitute those values into the expression we know to be true from the first part of the question that we answered, we'll have the square root of xy outside of the square root of x all squared plus the square root of y all squared is greater than or equal to 2 lots of the square root of x squared multiplied by the square root of y squared. Okay, so we can see some things here that are going to cancel. We're going to have these squared values cancelling with the square roots all over the place. So we can go and simplify that first. Okay, and we can see that we are very close to the statement that we're trying to prove. So the only difference that we have here is that the square root term is sitting in the wrong part. So we need it to be over the other side. So what we'll look to do now is move it to the right-hand side by dividing both sides by this surd. Okay, so we'll break the multiplication off and divide it away, leaving us with the left-hand side looking like we want it to, and the right-hand side giving us this expression, which if we are given a value where we have a surd in the denominator, the thing that we would do next to simplify is to rationalise that surd. So that's what we'll look to do. So we'll end up with 2 lots of xy multiplied by the square root of xy all over, and now we have on the bottom just an xy term, which will cancel with the term on the top, giving us the statement that we have been asked to prove. And we're done. Now if we have a look at this final question, again we have 2 variables that are positive or 0, and a statement involving square values where we can start, just as we have with the last 2, by considering the difference between them. So I'll start by bringing that expression that's sitting on the right-hand side over to the left and subtracting it from the expression that was already there. Meaning that now we are trying to prove that this expression on the left-hand side is a value that's positive or 0. So just as with the last 2, if we can bring this down to something that is able to be factorized into a perfect square, we know that to always be a value that is greater than or equal to 0, and it will therefore prove the statement for us. The other thing that we need to think about is that we're being asked to work with fractions. So as we do that, we also need to consider the things that we do when we are adding and subtracting fractions, such as making sure that we have a common denominator first. So in order to get a common denominator, I'm going to have to start by expanding this set of brackets. So we'll leave the first fraction untouched for the moment, and this second set of brackets will give us a binomial on the top and a 4 on the bottom. And that shows me that to obtain a common denominator, I need to double the values in the first fraction. And I'll subtract that from this entire second numerator. And now I have all of that over a common denominator of 4. Okay, so the next thing that I can do is now multiply both sides by 4, because I don't want to work with that fraction. And the nice part is that the right-hand side of my expression is 0, meaning that when I multiply the 4 across, it's gone, leaving me with this expression that I'm now proving is a value greater than or equal to 0. Okay, so we're still looking to be able to bring this thing down to something that will factorize into a perfect square. So let's expand the expression in front of us and this negative value to see what we have. Okay, so we can see that we have some like terms here that we can collect. So we've got 2a squared minus a squared gives us an a squared. we've got a 2b squared minus a b squared gives us a b squared. And then we've got a negative 2ab. And if we rearrange that a little, we can see that we now have an expression that will factorise into the perfect square that we're after, giving us a square value that is definitely greater than or equal to 0. And so we've proven that the statement holds true. And this gives us a little summary of ideas for when we are solving these types of inequality questions. So remember that we're looking to move everything to the left-hand side of the inequality and consider the difference between the two expressions that we're given, particularly if it allows us to then prove that something is a positive value. If that's the case, then we're going to look to simplify the expression that's on the left-hand side into something that will factorise as a perfect square, since we know that square values are always positive or 0. And don't forget about your work with fractions. When we're trying to add or subtract fractions, the very first thing you always must do is find a common denominator, and that will generally show you where you need to head with your simplification from there.